Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, this is the first lecture of first week. So, in this week as well as in the next week lectures, I shall cover a few relevant topics which are the prerequisites to understand this course. So, today we will discuss what is space environments and what are its types, what is space weather, and as the sun it takes a predominant role in the space weather conditions, we will discuss what is the anatomy of sun and what are the solar activities which act as a space weather driver. So, it is a basic question, what is environment and what is weather. So, everything that surrounds us, this is whether it is living or non-living objects, these are all environment. And what is weather? Weather means that is the state of the environment at a particular place during a short time scale. So, this is called the weather, as for example, the atmospheric phenomena like the temperature, humidity, then precipitation, the type and amount, air pressure, wind and cloud cover. Like if I say today is a bad weather, means it can be there can be rain or can be wind like that. And there is another definition that is called the climate. So, climate is whenever you integrate this weather conditions over a longer time scale over many years, then it is called the climate. So, now that is our topic is the space environment. So, we will try to understand what is space environment. So, the environment surrounding an orbiting spacecraft which is dictated by solar as well as the non-solar phenomenon. We will see what are the solar phenomenon and what are the non-solar phenomenon. So, why it is important this to study and to know about the space environment? Because when a spacecraft you are inducting into an orbit, when it is operating in an orbit. So, there are many types of the hazards that the spacecraft faces. So, there are the visible hazards like micrometeoroids, then orbital debris. Will in the subsequent lectures we will explain what is micrometeoroids, what is orbital debris, but these are the hazards which can be seen. There are the invisible hazards like highly energetic particle, highly reactive neutral atom, then radiation environment. So, these are all the invisible environment. So, apart from this the spacecraft it faces that is the atmospheric drag. So, what the atmospheric drag does? It deorbits, it tries to deorbit this spacecraft. Then there are apart from this there are interplanetary gravitational pull. So, that also perturbs its the orbital position as well as orientation. Okay. Then this spacecraft, whenever we place this spacecraft at that altitude, the air density is very low. So, that is called the near vacuum or vacuum conditions. So, there are because of this vacuum conditions, there are many challenges that we will be discussing, and then already I said this is the electromagnetic radiation also this spacecraft is exposed. So, this is so if you see a spacecraft is there are so many types of the environment this spacecraft has to operate properly. So, in this course we will be studying one by one all this. Of course, in this week and next week we will discuss a few relevant things. So, that let us come next to what is space weather. So, if I want to the formal definition of the space weather, it refers to the varying condition in the space environment near Earth that are driven by the sun and its changing magnetic field. We will try to understand how the sun and the magnetic fields are related, and space weather affects space as well as the ground based systems. So, you can see it from this picture, because whenever we do a communication like the wireless communication to satellite to the ground. So, these are all through the ionosphere. So, because of the varying space weather condition, there is changes in the ionospheric conditions, and that disrupts a lot of signal that is conditioning. So, to understand and predict the state of space weather, it is always necessary, and we will be also study first the sun and its activities. So, this is very important to understand what is the solar activities. Then interplanetary magnetic field. So, interplanetary magnetic field here I mean that is the magnetic field that is due to the solar system. Then there are some effects that is called the non-driven perturbations. So, there are non-driven non-solar, like there can be the galactic cosmic rays, and then the the atmospheric drag. Of course, the atmospheric drag is also a function of the solar activities. During when the solar activity is maximum, the atmospheric drag increases. Then planetary magnetic field. So, each planet like our Earth is having its own magnetic field. So, how that also takes into this takes an important role in this space weather environment that we will be studying. So, now what is the the difference between our terrestrial weather as well as the space weather? There are a few similarities, but mainly there are many that is that striking differences or dissimilarities. Like the terrestrial meteorological processes, they are highly localized. So, it is possible to make a good local the weather model for atmospheric weather. As for example, the atmospheric model of the Assam will be very much different from that of the Rajasthan. But the space weather events that occur over a wide range of time scales. We will see that is the Earth magnetosphere. It responds to the solar originated disturbances within only a few minutes, and the global reconfiguration occurs within some 10 minutes. And enhanced fluxes of energetic particles in radiation bands, that we will come to what is come to know what is radiation bands, Earth's radiation band. But just I am mentioning here, there are the radiation bands in the Earth's magnetic field. So, they decay in time scales from days to months, even longer. So, it is important to know that the space weather predictions that are based on the input from very limited measurements of the like we will come to that is a solar wind it is term. We will come to know what is solar wind and the observations. So, these are very much limited, it is not available in a localized manner. So, having those the data or whatever this information, that is having a global character instead of having a that is a local character like terrestrial atmospheric condition. So, therefore, the successful space weather activities aiming to make prediction of dangerous events need to be performed on a global scale. Generally, these things are made in a global scale. Now, since we told already that sun is it takes a it is a predominant role in deciding the space weather in the space environment. So, what is sun and a little bit information about sun we will discuss now. So, what is sun? Sun is basically, since it is a star, so it is a giant spinning glowing sphere of hot electrically charged gas. So, this is important word, that is it is a gaseous. So, you can see this picture, it is not like in a solid rocky, and it is consists of only charged gas or gas particles as well as the magnetic field, very high energetic radiation. So, what happens, this charged particles or the charged gas moves, and whenever a charged particle moves, it is equivalent to like a electric current. So, whenever there is an electric current, there will be the magnetic field by Ampere's circuital law. Sun has a diameter approximately 1.4 million kilometers, which is about 109 times that of Earth, and Sun has 3,33,400 times more mass than that of Earth, and it contains 99.86% of the mass of the entire solar system, and its distance, that is, it is 150 kilometer or 8 light minutes away from the center of the Earth. And it is important to know that in each second the sun loses 4.55 million tons of material. So, this high loss of mass is insignificant when you compare it with the total mass of the sun. So, over the past 4,500 million years, it has barely lost a few hundredths of the percent of its total mass. So, what you can say, it is even less than 0.1% of the total mass the sun is having at its core. Sun rotates on its axis once in about 27 days. The sun's rotation axis is tilted by about 7.25 degrees from the axis of the earth's orbit, and this rotation, that is this period is not uniform. So, sun rotates faster at the equator than at the pole. So, here it is 25 days. So, this is called the differential rotation, and for that also there are some phenomena happens that we will explain subsequently. So, whenever if you want to observe the sun, so since sun emits the electromagnetic spectrum at various wavelengths, and you cannot have any observatory which can using one observatory you can have the picture of all the wavelengths. So, that is why you will find that the sun, whatever the image is, the color is different. So, just you can see. So, if you take only this image where only the wavelengths related to the radio frequencies, you will get the picture like this. If it is X-ray, then it will look like this, then infrared, and then ultraviolet. So, these are this information about the solar system. It is obtained at different wavelengths using different types of the telescopes. So, now let us see what is the structure of this, what is the inside the sun. So, basically the sun consists of so many layers. So, the first one is the core. So, core generally mainly it contains the hydrogen and helium, making about 98% of the total mass, but other heavier elements like iron and these things are also there. They play important role in the physical process that occur in the core of the sun. So, physical process means basically it is the nuclear fusion it happens. So, we will come to that in the subsequent slide. So, you see this is the core, and in the core there is because of the nuclear fusion the mass is converted into very high energy. So, basically a nuclear explosion happens inside the core of the sun, and then that energy it flows outward to a region. This is called the radiative zone. So, this is this zone. This is the radiative zone. So, this layer radiative zone is just outside the sun's core, and it transfers the core's high energy nuclear explosions and the resulting plasma. We will come to again explain what is plasma. So, this we will be doing one by one. To the convection zone. So, next layer comes, this layer is called the convection zone. So, here it shows this is the convection zone, this one. So, convection zone through radiation. So, next what is convection zone? So, the region inside a star, means here in this case it is our sun, where the energy flows outward using the process of convection. Okay. So, convection means it is going from higher to the lower temperature. The particles are going from higher to the lower temperature. Then the next layer, which we can see it, that is the only part which you can see from the earth without use of any specialized equipment. So, this is basically through visible all these visible lights come from the photosphere. So, we can see it even with our bare eye. Then the next layer, that is the chromosphere. So, chromosphere, this is a irregular layer that will come to know that why it is irregular layer above the photosphere, where the temperature rises from 6000 Kelvin. So, say around 6000 Kelvin, or it is something like 5800 Kelvin temperature to about 10,000 Kelvin. So, this is something it needs to be explained, because generally the flow of energy it should happen from higher to lower, but here it is the opposite case is happening. When you are going away from the sun, the temperature is increasing. Then the next the outermost, it is also called the atmosphere of the sun. So, this is the corona layer, the outermost part of the sun's atmosphere. This is usually hidden by the bright light of the sun surface. So, we cannot see it the way we can see the photosphere without using the special instruments. But this corona can be viewed during a total solar eclipse. We will come in the subsequent section when we will discuss more about the corona layers. So, the sun's core is the central region where the energy is generated. How energy is generated? The energy is generated by the fusion of two lighter particles, that is the hydrogen, to form a heavier particle, that is helium. So, the hydrogen is converted to the helium, whose mass is smaller than the mass of the constituents. The mass defect being transformed into energy. So, this is that energy conversion, that is that the relation which was given by Einstein. So, E is equal to delta m c square. So, we can have just an example of the same example, that is the 4 hydrogen atom is when it is after the fusion, when it become helium, what is the mass difference. So, let us, so the same example. So, we will consider just consider the fusion of H into He. So, the mass of H. So, this I can write 4 into 1.008145 AMU, atomic mass unit. The mass of 4H. So, this is equal to 4 into 1.008145 AMU. The mass of the helium atom is 4.00387 AMU. So, now we can calculate the difference in mass. So, difference in mass will be 4 into 1.008145 minus minus 4.00387. So, this will be equal to, so this I can write, this is equal to 0.02871 AMU, 4.768 into 10 to the minus 26 G. So, now we can calculate the E is equal to, so this is my delta m. So, E I can calculate delta m into c square, and this I can show it to be 4.768 into 10 to the minus 26 G multiplied by 3 into 10 to the power 8 meter per second, and the whole thing into square. So, this if we do after this calculation, I can show this is equal to 42.912 into 10 to the power minus 6 gram centimeter square per second square, and then this I can write as 4.291 into 10 to the power minus 12 joule. Okay. This I can write as into joule, and which I can convert into in electron volt. So, 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So, I can convert it into electron volt, and I can show this is equal to 26.72 mega electron volt. So, if we assume that sun consists of pure hydrogen, which is converted to helium, then the total energy is 7.9, approximately 7.9 to the power 10 to the power 58 mega electron volt. You can see what is the huge number. So, as we have seen, the energy generated, the huge energy is generated in the core of the sun, that outward through these different layers, which already you have seen, and finally through the atmosphere, outermost layer, that is the corona. It comes out from the outermost layer, that is the corona of the sun. And this process, it takes 1000 years or more, and the radiation which the radiation itself take 1,70,000 years to make its way from the sun's core. And already you have seen the photosphere, that is layer is the temperature is 5800 degree Kelvin, whereas the chromosphere it is about 10,000 Kelvin, and corona it is even, however, it is 1,000,000 degree Kelvin. So, in summary you can see these are the layers of the sun core, then radiative zone, then convection zone, then photosphere, then the chromosphere will come and the corona. So, if I compare this with just as a I can compare this with this. So, as if the energy is generated, something you are heating, you are giving the energy, and so that energy is something like what is that explosion, nuclear explosion is happening here, then that energy is getting to that this upper layer through the radiative process, and then you are having the convection zone. And on the photosphere here you can see these some loops, these are all the magnetic loops. So, these are called the sunspots. So, we will see that how the sunspots is related to the sun's activity. So, what are the sunspots? The sunspots they appear as some dark spots on the surface of the sun, and since they appear on the photosphere. So, these can be visible by the telescopes, by the ground based optical telescopes, and the sunspots that can typically stretch from 1000 to some 100,000 miles across. So, the sunspots are caused by the sun's magnetic field, and the sunspots can be seen on the sun's photosphere or the visible surface of the sun. So, this is seen, you can see this is the picture or the image. So, you can see there are so many spots. If we zoom one spot, so we get something like that. So, it is one spot is very dark and surrounded by lesser darker space. So, that is called the darker space is called the umbra, and the surrounding place is called the penumbra. And then you can see this magnetic field lines are coming out of that the dark spot, and this magnetic field lines then they end to the nearest sunspot. So, basically the sun is made the plasma. Plasma means it is a charged gas or ionized gas or electrically charged gas. The electrically charged gas can affect the magnetic field lines, causing the lines to twist, that we will see, because there is the sun, there is the differential rotation, and because of this sunspots their number also vary. So, in that case this magnetic field lines they twist, turn and tangle as the plasma moves, and because of this there are so many sun activity happens that we will see one by one. So, you see, because of this what I said, that the sunspot to sunspot is as if the magnetic loop is there, and since the earth there the sun there is the differential rotation, this magnetic fields because of this phenomena like twist, turn and tangle. So, that gave rise to this form of that is this magnetic activities, or that is the strength of all those magnetic fields that vary over a period of cycle, that is called the sun cycle. So, what is sunspots and their cycle? So, these sunspots they increase or decrease through an average cycle of 11 years. So, if you see that is dating back to 1749. So, we have something like 23 full solar cycles, where the number of sunspots have gone from a minimum to maximum and back to the next minimum through approximate 11-year cycle. So, this is called the sunspot cycle, 11-year cycle. So, you can see here, so it is going from minimum to maximum, the minimum to maximum, and you can see there are something like 23 cycles here over the period of last how many years, from 1749 till date. So, so many that is this that is 11-year cycles has happened. So, during the maximum of the cycle, you can see the maximum of the cycle, even the maximum, that is the number of sunspots which can be seen on the surface of the sun, it can vary even up to the 100. During the minima, the suns sometimes does not have any spot. This cycle is closely related to the magnetism of the sun. In fact, it is the changing magnetic field of the sun which governs many aspects of the solar activity, that we will see one by one. So, now what are the solar activities? So, sunspots are the visible component of the active regions, areas of the intense and the complex magnetic fields of the sun, and these are the sources of the solar eruptions. Because of the solar eruptions, there are the phenomena like solar flares, that we will explain one by one. Solar flare, then coronal mass ejections, which are typically the burst from these active regions. So, these are very important, that is why the scientists they study the regions where this activity occurs, and because of this phenomena, this drives the space weather, which can impact the spacecraft, astronauts and the infrastructure on the earth, which we just mentioned at the beginning. So, you can see this is the solar, these are the explosion or the eruptions that happens on the outer surface of the sun. So, sunspot groups are often associated with active regions. The solar energetic particles, which is called the SEP, that also will explain in subsequent lectures. So, these are considered as a mass emission, but they are emitted during the solar flares and the CMS. Both the mass and electromagnetic energy output of the sun vary over a wide range of time scales and introducing disturbances on the space environment, and extends from the sun through entire heliosphere, including the magnetosphere and the ionosphere and the planets and the moons of the solar system. Solar flares, coronal mass ejections and the high speed solar wind and the solar energy particles are all, this is the forms of solar activity. So, when I say the term, that is what is solar activity means the phenomena like solar flares, coronal mass ejections or high speed solar wind or solar energetic particle events. So, these are all called the solar activity. So, we will see that this how the solar activity is called as a driver of this space weather, because during this phenomena like the solar flares or coronal mass ejections, there is a lot of that is energetic particles or the radiations that is produced in the sun's atmosphere, which eventually it reaches to the earth, and then it couples to the earth's magnetic field. So, this is called the geomagnetic storm and geomagnetic substorm, that also we will study one by one. So, interplanetary magnetic field and the radiation through which our spacecraft journeys around the planets of the solar system. So, that also we will see. I think let us end here, and in the next class we will again we will start from here and we will explain, we will deal with the corona layer of the, that is the atmosphere of the sun, and we will explain the corona, what is the coronal holes and the subsequent topics. Thank you very much.